Hey guys, this is our last lesson over this chapter, so hopefully things are starting to come into focus for you about how circuits work a little bit and the math involved. I'm going to be using the same formula sheet that I made in the last one, so if you did not get these formulas written down last time, again I would encourage you to have these handy while you're working on these. There's these, and then one more at the bottom. So again, I encourage you to pause and make sure you have those written down before we try to do any of these. Okay, so this is, should say 17.3 power at the top. Formulas are not new, but we may be using them in a slightly different way. Okay, so the examples are already written out with answers, so hopefully you can focus on me and not look at what the answer is, and we hopefully will get the same answer that they got. That's how we know we did it the right way. Okay, so the heated side mirror in Bryce's car has a resistance of 4 ohms. Remember that Greek symbol omega there stands for the unit of resistance, which is ohms. How much battery current do the heat coils draw when they run off the car's 12-volt battery? So we have resistance here, and a voltage, and we're trying to get to current. Looks like this equation is going to be our best. All right, that has all of the things we're trying to work with here. We have voltage equals current times resistance. So voltage is my 12 volts equals current times resistance. Don't forget the value of writing out your work. I've noticed a few on the assignments that we have had turned in, you just have writing down an answer, and it turns out if you don't write out your setup, you're very likely to multiply when you should divide, or divide when you should multiply, or divide the wrong way. So just remember, just like we've been doing all year, it's worth it to write your work out. So my unknown is times 4, so on the other side I'm going to divide by 4. 12 divided by 4 is 3, and my unit for current is capital A, or you can write out the full name of the unit, which is amperes. So either of those works. Then we have a secondary question. How much power do the coils use? So now we know voltage, resistance, and current. We're trying to get to power. We look back at our equations and we say, okay, we're looking for power. Remember, we have 3 ways we can calculate power. Looks like the only one we can do is this one, current times voltage. So power equals current times voltage. So power is current is our 3 amperes times voltage, 12 volts. So power is 12 times 3, which is 36, and we have to think about what kind of unit do we always put on power. Power is watts. Okay, so let's see if we agree with what the book came up with. They got 3 amperes, and they got 36 watts. Oh good, we did it right. Alright, let's try example 6. A 12-volt outlet in Carol's college dorm room is wired with a circuit breaker on a 5-amp line so that students cannot overload the circuit. So we know voltage and we know current. If Carol tries to iron a blouse for that class with her 700-watt iron, will she trip the circuit breaker? So we have, remember, watts is power. So we have power, current, and voltage. Trying to find an equation that includes power, current, and voltage. There we are. Power equals current times voltage. So 700 is the power equals current. Well, that's not quite what I want to do, is it? I was just trying to make that a lot harder than it was. So the 5 amps is not necessarily the current. Okay, the 5 amps is the maximum current. Okay, so if we calculate the current to be more than 5, then yes, she will trip the circuit breaker. So we're going to use the same formula I had worked out. So we have power equals current times voltage. Here's 120 volts. Okay, so my current, my unknown, is times 120. So I'm going to take 700 divided by 120, which is 5.8 amps. Okay, so for everything to work out for her iron, she'd need 5.8 amperes of current, which is too much. It's maxed out at 5. So would she trip the circuit breaker? Yes, because she's putting more current through than it is designed for. And then we have what is the resistance of the iron. We only have one equation with resistance. Voltage equals current times resistance. So we have voltage equals current times resistance. Resistance is 120 divided by the current that would be trying to go through. Looks like 20 ohms. Okay, so let's see here. So they said, yes, she will. See opposite side for more details. Looks like they kept one more significant figure, but 20.5, 20, basically the same. All right, we have one more example that they solved out for us, so we can test our math without taking up any of your valuable questions that you get to actually do. The Garcias like to keep their 40-watt front porch light on at night to welcome visitors. If the light is on from 6 p.m. until 7 a.m., the Garcias pay 8 cents per kilowatt hour. How much does it cost to run the light for this amount of time each week? Okay, that's actually just kind of telling you how to do it. So we're going to figure it out together. So we have watts, which is power. We're given some times. All right. So if we have a power and an amount of time, we're looking at power equals work divided by time. But when we start talking about charging people for electricity, remember the people are generally charged by the kilowatt hour of energy used. Okay, so we probably would like to convert this amount of watts into kilowatts. So that would be the power of their front porch light. And we're going to figure out how many hours it is each night. And then we're going to figure out how many hours it is in a week if we leave it on that many. And then we would know the kilowatts and the number of hours. And again, I plugged a 1 in there. It doesn't have to be. And then we can figure out how many kilowatt hours. And then we can take it times 8 cents. So we have a whole slew of steps to try to figure this one out. First thing I'm going to do is go from watts to kilowatts. Right? So there's 1,000 watts in a kilowatt. So 40 divided by 1,000 would give us 0.04 kilowatts. Okay, so now we know the amount of kilowatts. Now we need to figure out the number of hours that it's going to be on. So from 6 p.m. till 7 a.m. All right, so if it was from 6 p.m. to 6 a.m., that'd be 12 hours. So it's 13 hours, right? 13 hours times 7, times we're going to do that for 7 days. So 13 hours, because they said for a week. So 13 times 7 gives us 91 hours. All right, so we look back at our equation. Now we have kilowatts and we have hours. So we're ready to use kilowatts equals kilowatt hours divided by hours. Okay, so I'm going to go 0.04 kilowatts equals kilowatt hours divided by 91 hours. Kilowatt hours, my unknown, is divided by 91. So I will multiply by 91 and I get 3.64 kilowatt hours. Okay, remember that's that weird unit. Even though it's made of a unit of power and a unit of time, it is a unit of energy. Okay, and our problem says for every kilowatt hour, they get charged 8 cents. So we're going to take that many kilowatt hours times $0.08. Right, that's how you would write 8 cents in dollars. So we go 3.64 times 0.08. So they're going to get charged 29 cents about to keep that porch light on for a week. See if we agree with our answer here. Oh, good. Oh, no, that's 29 cents. 8 cents. Oh, that's the same thing. I said 29 cents. Gosh, brain fart. Okay. So a couple things I want to point out to you guys before we go again. On number 11, their wording here, I looked at it and I thought it might confuse you. It says, what is the voltage drop when the air conditioner is running? Remember, voltage is just the potential difference. Remember, difference means subtract or how much it drops. So just, if you want to cross out that word drop, it doesn't make any difference. Okay, so you're basically saying what's the voltage when the air conditioner is running with that much current and that much power. Okay, so don't let that word kind of mess with you. And then when we get to 12, and I believe 13 you need to also, but I just kind of want to remind you, you're going to have to use more than one equation. Okay, so first thing you're going to need to do on 12 is find the current. Once you have the current, then you can plug it into this other equation and find the resistance. And then on 13, I'm going to make letter C bonus. So give it a shot. Worst thing you can do is it doesn't hurt your grade. Best thing you can do is you get a bonus point. And on 14, since I'm not there to remind you in person, remember kilowatts is equal to 1,000 watts. But just like the one we just did, we might want to leave it in kilowatts because we're going to end up trying to calculate the kilowatt hours, and it's going to be a lot like this one we just did where we're going to find the kilowatt hours and then take it times the amount that is charged per kilowatt hour. And I think that's all. If you have any questions, as always, let me know. Be happy to Google Hangout chat with you or video chat, whatever you need to hopefully get this all figured out. Good luck. Talk to you later.